Right, okay, good morning, and thank you for the invitation to come along here. There are a few people in this room I've worked with before on different projects, but many of you I don't know. So as David said, I'm the director of the SUPERGEN Bioenergy Hub, and it was interesting to hear you say that you hadn't actually been involved in the writing of the proposal for the network, because we find ourselves in a somewhat similar position here. Like 3 years ago now, I did write the proposal for the SUPERGEN Bioenergy Hub, which we submitted to EPSRC, and that funded 6 partners in academia and I think 7, maybe 8 industrial partners to do, let me get this right, 12 projects. And that was set with our original £4.5 million worth of funding. Since then, EPSRC have run a number of challenge projects, so periodically we get told, and by the way, you need to integrate this as well, and this one, and this one. None of these we've had anything to do with in the preparation, so suddenly you're faced with the challenge at the moment of having 18 academic organisations, 13 non-academics, an advisory board, which thankfully we did put in place and is entirely policy and industry focused with 15 other people, and trying to bring all of those together with a 12.8 million portfolio of funding to do something sensible in the UK energy space. Now that is quite a challenge, so I really sympathise with your issues here. I think the complexity is actually very similar, and some of the discussions we were having last night and this morning have made me realise that actually some of what you're trying to do here I think is very, very similar to some of the higher level objectives that we have in the hub. So yeah, so I'm based at the Tyndall Centre for Climate Change Research. I sit within the School of Mechanical Aerospace and Civil Engineering. I'm technically a chartered physicist. You probably wouldn't know that if you looked at some of the things that I've published recently, but that's the space we sit in. And my background is that prior to being in academia, I spent my time in industry working as a combustion engineer on large power plants. So that's where I come from. And I think that's important because David's mentioned already the relevance to your network of engaging with policymakers and engaging with people in industry. And the reality that I'm going to put up in a moment about climate change and the environmental issues we're trying to address is that academics, in one sense, sort of hold all the keys. You've got all the information and you've got all the methods that we can use and the techniques, but unless you actually use them, it doesn't make the slightest bit of difference to the planet that we live on. So it's really, really important that we do this great work and that we're interdisciplinary and that we connect with people and get this holistic picture. But if there's one thing that I really want you to remember from what I'm going to say in this presentation, it's that unless you get that message out and you connect with your industrial partners and you connect with the people making the policy decisions, you might as well not have bothered. Okay? Right, so an overview of what we are going to go through in this presentation. I'm from a climate change centre. I can't come here and not talk about climate change. I know many of you are well versed in this, but I'm going to remind you that it's important. We're going to talk a little bit about greenhouse gases, but then move on from that. And actually, greenhouse gases are one dimension, and we talk about some of the wider environmental trade-offs that get brought up when we try to minimise greenhouse gas emissions. This is particularly played out in the area that I do most of my work, which is bioenergy. I do other work in other areas on sustainable energy systems, but bioenergy is quite fascinating because of the complexity of the trade-offs and the level of interdisciplinarity that's involved when we look at the whole systems. I'm then going to talk a little bit about uncertainty, which is really, really important, particularly when we're looking at trying to guide policy issues moving forward, and methods that we have in the environmental sector for dealing with that. I want to take a step back on item number 4 and say, well, what do we actually mean by sustainability? You've mentioned it this morning. It's a word that we use a lot. When I wrote the proposal for the hub, I think I had the usual 8 sides of A4 that you're allowed to submit to RC UK. And after it got funded, because it took a long time, I went back and I read it all again, and I was amazed to realise that nowhere in the entire 8 pages had I used the word sustainable or sustainability, not once. And it would be almost untenable now to put anything into the research councils in the energy sector and not have that word and not have it badged. So it is something that is really, really important, but I think we often use the word without thinking about what it really means. So I want to take a little bit of a step back and say, actually, what's your definition of sustainability, and how is this network framing that when it looks at what it's doing in Wales and what the impact of that will be elsewhere? And finally, I want to make that connection through to policy. I have a very nice example, which is rather timely. It's a piece of work I have at the end of the presentation, which actually just got accepted by a journal 2 days ago, so this is right up to date. It's a nice example of collaboration, but it's also actually very relevant in this policy and uncertainty space. So we'll go through those technically for the sort of environmental energy interest of the whole thing, but I want to use the examples of the different outputs that I have for you to also show the ways of working that we've developed in the hub. Because like I said, we are these different academic organisations, some of us strategically together, some of us thrown together, policymakers, industrialists, and there are different types of outputs and different ways of working that are effective for some of the different objectives that we have. And I think we're probably about 2 years ahead of where you are in terms of establishing the network and trying to work out what we should be doing and how we pitch things and pitch our resources to make that the most effective use of what is at the end of the day public money. So I want to share with you as we go through not just the science in some of these, but how they came about, and maybe have some suggestions, particularly I was having conversations with Surinder last night about the sort of things you might think about doing as you try to make your network an effective mechanism. Okay, so let's start with the climate change. This is a slide we use a lot in the Tyndall Centre. We use it for our undergrad students, we use it for our MSc students, and it's really aimed at showing the whole picture, the climate change issue, everything that's going on. And all of these different boxes that you see in the different arrows are all physical, chemical processes which we have a scientific understanding of and we can fairly well define. We can build up equations and we can do calculations and run computer models that will calculate all of these. And that's what we teach our students in the undergrad and postgrad courses. And we tell them that greenhouse gases are important, they absorb radiation, and therefore actually they maintain the climate that we have. There's this perception that they're actually negative. They actually provide us with the climate that we need in order to survive. They've been doing that for a long time, but as we all know, anthropogenic activity has caused them to increase massively over the last 100 years. And then we tell them that based on all these calculations which we can do, run these nice computer models, and I know there's some people in this room who are involved in these calculations, then we can tell people that the global mean surface temperature will increase by around 1.2 degrees centigrade if we just look at the greenhouse gas issue in isolation. And then we make things more complicated. We look at some of the other factors that were on that previous slide, and we say, well, actually, there's a lot of things that we're not sure about, that we're still looking at. There's, when we take into account all the feedback loops, actually the warming could be anywhere between 2 degrees and 6 degrees. We have a lot of uncertainty around the role of aerosols in the atmosphere, yes, because they reflect the sun's radiation back into space, and it might be a good idea to reduce the amount of aerosols which we're emitting, but then what would happen and how would that balance pan out? How will CO2 sinks perform in future? The ocean is a big one here, but also as we have melting and we have different land areas being uncovered, how do those exchanges change under the future climate that we're projecting? Clouds, incredibly complicated, and can have quite a significant impact on the results that come out of this. Surface albedo, I mentioned the ice melting and the impact that that has, but also the level of forestation that we have has an impact there too. So there's a lot of things that we can project and model and that we know, and our scientific understanding goes into this, but there's also a lot of uncertainty still out there, which gives us these bands that we work within. And what that results in is scenarios that we've done a lot of work at on Tyndall on where we'll be in the future. And we talk a lot about whether we might end up in future with a climate that is sitting in a 2 degree C world or a 4 degree C world. And when we talk about at 4 degrees C, what we mean is that the global mean surface temperature has increased by 4 degrees centigrade. It's important to realise that the reality of that, because 4 degrees centigrade, when we're sometimes sitting in not very clement weather, we can think actually 4 degrees centigrade would be okay, wouldn't mind that. But the reality is that the hottest days of the year will increase by very much more than that. And that will depend on where you live. And in some parts of the world, they may go up by 6 degrees, in some parts 8, but some of the regions down at the bottom here, we may see increases of 10 to 12 degrees centigrade for the hottest days compared to what we have at present. And that's really quite challenging when we look at adaptation and resilience and how our existing infrastructure and livelihoods would continue to function in that sort of world. Sea level rise. Again, I'm taking the 4 degrees C pathway here, and we could be looking at 80 centimetres of rise in certain parts of the world where it will be particularly significant, where we can be wiping out areas that people currently live on and currently have livelihoods on, and then you have the impacts of that because the sea level, even if you count not just the loss of land, but the impacts that has on salt, on areas which then become uncultivable nearby. Droughts, this is a big one. 1 in 10-year droughts will become twice as frequent in all those places marked. The one that bothers me here is down in the bottom, because this also happens to be one of the areas where our population globally is projected to expand massively by 2050. So we're looking at a doubling or more of population in that region at a time when food security is sometimes already in the balance, and then we're looking at a 1 in 10-year drought, which can tip over the edge to cause massive devastation in those regions, and that becoming once every 5 years. And then we start thinking about the impact of that on those individuals, but also the capacity that we have globally to be able to respond to that. Extreme weather events are much, much harder to project. The climate models work quite well at projecting the average temperatures and the things that we can see happening in the long term and the mean figures. It's extremely difficult to predict the extremes that we will experience in the future and the increased likelihood of those, but we know that there will be increased numbers of heat waves, increased drought, increased heavy rainfall and storms, and that will lead to increased flooding risk. So, lots of threats there, and rightly you would think that we would have a political imperative here, and there is a cross-party consensus. I was reassured of this again by DEC on Friday, that no matter which party gets in, there's a cross-party consensus that we have this commitment and we are committed to stabilising greenhouse gas emissions at a level consistent with avoiding, quote, dangerous climate change. Now here we enter the blurred world a little bit, because my definition of dangerous climate change might be quite different to that of our next energy ministers. We'll have to see. But what we've done in terms of policy, and I think it's important to realise here as well that the UK on its own isn't a signatory to most of the international policy agreements on this area. It's the European Union which signs up to the Kyoto Protocol and other documents. And then the target that they agree is distributed across the member states. So in some ways, we have to give credit to the UK politicians who, despite the fact that they're not direct signatories to this agreement, have actually put in the Climate Change Act, which gives us a statutory commitment on climate change. And I think, respect where it's due, they have been one of the only countries to do that and to move in that direction. So I think that's a sign of how important that it's seen to be. And the target is that we're going to reduce emissions to avoid global mean temperatures rising by more than 2 degrees centigrade. Now, many people who run these climate change models would say we've already passed that point. We're looking at whether or not we can avoid 4 degrees centigrade. 2 degrees is fairy tale stuff. But even if we accept that we're only trying to do the 2 degrees centigrade one, let's look at what that really means. This is the target which the government has set. They've said that we'll have an 80% cut compared to the 1990 level of emissions. And these figures on the left that I've given you are our emission levels in 2006, which were a little bit lower than 1990, hence we only have a 77% cut. And in that year, we emitted 695 million tonnes of carbon dioxide. The target that the government has for 2050 is on the right here, 159 million tonnes. Now, every time I look at this graph, and I look at it a lot, two things jump out at me. One is, wow, that's a massive reduction. You just can't get away from that. But what I find more disturbing is you can't do the thing on the right unless you do something in every single one of those sectors on the left. Because a long time ago, back in the 1990s, I would say that the government in the UK really woke up to the idea that we were rather behind on renewables and we needed to do something about our energy system. And I was appointed back then to a ministerial advisory board. We were called the Renewables Advisory Board, and we had these lovely meetings from time to time with the minister, and it was all very nice. Trying to get that discussion to move beyond the word electricity was a major, major challenge. For a good 20 years, the UK's energy policy was really electricity policy. And in some ways, that reflected the infrastructure and the mechanisms that we had, because electricity is easy to deal with. It was centrally dispatched and we could collate all of the data and we could move with the key players. But it sort of misses rather a lot of the picture, because electricity is only 184 million tonnes. It's less than a third of our total emissions. Now, we have moved on since then. We were effectively forced by European targets to try to do something on the transport side, and I don't think I've got time to go into the sorry debacle that was the renewable transport fuel obligation. I'll happily talk to anyone about that later and the history on it. It's a good case study, actually, in how policy can sometimes move ahead of scientific knowledge and the very negative repercussions that can have. The desire to do something becomes very strong, and therefore we do things which we're not necessarily fully informed about. And that was quite a fascinating period when we went through that. We've more recently moved to the next level up. We now have a renewable heat incentive. I'm actually at a meeting in London on Monday where we're examining the role of biomass in that renewable heat incentive with a parliamentary group. So we're realising that actually quite a lot of our emissions come from the residential and commercial heat sector. And that one is rather important. And even if we addressed, let's suppose we somehow managed to make all of our electricity carbon neutral, whatever that may mean, and we got rid of those 184 million tonnes, and if everything in the transport sector was electrical, and we were functioning off all of this lovely carbon neutral electricity, let's assume that we can have a grid infrastructure that can cope with that, which I don't believe we have, then we've still got 103 million tonnes associated with heating there, which is well over half of what our total target is. So we need to do something about that. The one above it bothers me even more. Industry, industrial heat and industrial processes. I've done a fair amount of work over the last few years with different process industry groups in the UK. Particularly, we work on Teesside with the North East Process Industry Cluster. And one of the things I hear again and again there from people who are actually producing bulk chemicals and producing materials, steel manufacturers and others, is that they have these targets thrust upon them and incentives to reduce energy consumption and reduce CO2 emissions. And what the impact of that actually is that we reduce the competitiveness of UK industry in this area. So we make it harder and more expensive for people to continue doing what they used to do. And this doesn't necessarily result in having any lower carbon production. What this results in is us importing more materials from overseas. So what we've seen happen, for example, we've had a lot of increase in photovoltaic deployment in the UK. Over 90% of the photovoltaic panels which have been going in have been produced in China, where the mainstay in terms of emissions is actually coming from coal. So some of the measures that have been put in place to try and curb industrial emissions have actually been rather counterproductive. They're great for the UK meeting its targets because the industry simply closed down or reduced throughput, and therefore our CO2 emissions go down. But we still need the materials, and instead we import them from overseas. John Barrett from Leeds had a report issued last week where the headline was that the UK CO2 emissions aren't coming down at all. When we take into account the embodied CO2 in all that we import and take a supply chain approach, we're actually increasing because we keep importing from China, India and elsewhere. So while I agree that we need to meet these targets and targets are important, we also need to remember that meeting that target isn't necessarily doing anything for global CO2 emissions if we're still consuming the product and it's instead being produced elsewhere. So we need to make a much more holistic view of this. And I'll just briefly mention a particular issue in this area, which was the main topic of discussion at a meeting I was at last week at Chatham House, is that there are a whole host of countries who don't have binding targets under the Kyoto Protocol. For those countries, many of them are developing countries, and it's quite right that they shouldn't have binding targets, but what that means is that their emissions don't actually get counted in the mechanisms that we currently have in place. And this is a real issue. So it's really important to say, yes, as the UK, we should be doing this, we need to do this, and I'll show you in a moment we need to do more than this. But it's important that we also think about what the consequences are of achieving that, and are we actually just displacing the problem elsewhere? Because in my mind, if we're actually importing goods from other seas, that's exactly equivalent to exporting our obligation and saying, we can't be bothered, we'd like you to do it for us instead. Okay, so I've mentioned already 2 possibilities in the future. 2 degrees centigrade, probably not going to get there. 4 degrees centigrade. This is work by colleagues of mine in Manchester, Alice Bowes and Kevin Anderson. And what this reminds us of is that carbon dioxide and the greenhouse gas emissions that we have are physical units of material which gets emitted into the atmosphere. When they go up there, they stay there for a long time and continue to exert their radiative forcing throughout their lifetime. Now what that means is that the actual global warming impact is nothing to do with the endpoint target that you set over here for 2050. What is important if I want a climate that is either 2 degrees or 4 degrees is not the level on the right, it's the area under the curve. It's the integral, the total amount of emissions over time that we have emitted. So the top line, the red one, would see us on a path that would have 4 degrees centigrade average warming over the planet because of the area under the curve. The right one would have us on a 2 degrees C pathway. Now let me flick back to the previous figure. You can see if I just sit at that 2006 number there, we're around 700 million tonnes. That is exactly consistent with the figures that the government had, 695. But we said we were setting a 2050 target, and this is statutory, of 159 million tonnes. 159 million tonnes, I forgot my pointer, is about here. So what that equates to is almost drawing a straight line from back there. So we, in our opinion, we may not meet the 2 degrees C figure with that 150 unless we have a very steep trajectory and we decrease our emissions very, very soon. If we come off on a cliff edge in the next year or so and we have a really steep reduction, then yes, we can probably do that 159 million. If we don't, if we do what we've been doing for the last few years and sit plodding around that level and then decide that actually we can do it by 2030, 2040, we actually need to get down to a much lower final target. We need to be going way beyond that 159 million tonnes and getting to practically zero on that unless we act very, very soon. So there are 2 things that are important there. The net greenhouse gas balance is important for electricity systems and energy systems when we're considering the environmental impact, but the timing is also important. We cannot delay until 2040 and do it all then. It will be too late. Timing is also a particular issue when we look at some renewable energy technologies where we require a big energy hit at the start, where we're perhaps trying to produce a photovoltaic panel in China with coal and we're having to consume a large amount of electricity or a large amount of coal in order to get the benefits in future. So we need to consider the net balance, and we have gradually built up a methodology around life cycle assessment, which tends to do that, but it does that based on normally a 25 to 30 year period, and it considers that as a whole block, and it looks at the net balance within that 25 to 30 year period. If we look at the net balance over 25 to 30 years, we may still be exerting very significant emissions during the next 5 years, which can still mean that we have to cut harder and longer in the long term. I hope that makes sense, because it's really important. At the bottom here, I've just put some really quite basic examples. This is some work we did a number of years ago to illustrate the differences that you can get if you go up the supply chain on greenhouse gas balances. So this was work looking at biodiesel production at around the time the RTFO was being put in place. And it was showing that really just at very high level the significance of land use change. So if you have land that was converted from cropland, you end up with a carbon debt, which is practically non-existent. So you can start paying back almost immediately. If you've converted from grassland on the right-hand side, the carbon payback period is 55 years. You have to go 55 years down the line before you're actually being net positive in terms of your greenhouse gas balance. Now, from that target I showed you previously, that is completely pointless. 98 years if you convert from forest land is even worse. So the emissions are important, but be very, very careful to look at the time period and realise that the timing of those emissions is also important. Okay, so lots of people, I'm sure, in your network doing this sort of work, which we've done as well on greenhouse gas calculations and greenhouse gas balances, and they are important. And this was work, like I said, that we did on soy coming from biodiesel. I don't think I've got the other slide that I normally show along with this. I was trying to be quick in this presentation. But one of the interesting things here is that these two options, A and B, are for completely different production mechanisms for soy in Argentina. One is a very large-scale no-till system using a genetically modified crop, and the other is a more traditional system. What is interesting is something that leads into the next slide about trade-offs, is because the option which gives you the best carbon reductions is the one that actually gives you worse impacts in terms of biodiversity and ecosystem impacts. The reason for that isn't necessarily obvious, and it's tied up a lot in human responses and social issues. Because the reality of what has happened as GM crops have become more established in many of the Southern American states, and particularly in Argentina, is that you provide farmers with something and you say, have this, and you can spray your herbicide because it's herbicide resistant, and you will get these improved yields. And the farmers, in reality, during the period since the GM crop was introduced, massively increased the amount of herbicide they were actually using. That wasn't in the guidelines. They weren't told to do that. It just seemed like a good idea because it was made available, it was cheap, and it was something that was a human decision to actually go down that road and do it. So it's quite fascinating that in theory, you wouldn't get this massive trade-off. You would get a small increase in the ecosystem impact and the reduction in biodiversity and increase in terrestrial ecotoxicity. The reality is when you implement it and you put people into the equation, you get a much greater impact. So that's one of the other things that I really wanted to say to you this morning. Environmental science, great. Turn it into the practicality with the engineering side, fantastic. The social sciences and the social responses to the mechanisms that we put in place are also really, really important because people have rather habit of behaving in the way that you wouldn't have thought. Okay, so I'm going to come on to some other environmental impacts and trade-offs. I've already mentioned that the best and most carbon effective way of producing biodiesel from soy will give you the worst impact in terms of ecotoxicity. This is some work that was done on production of biomass, and this was done in the SUPERGEN consortium with work between Manchester and Rothamsted Research. And this really just involved taking data that they had on how they were growing different energy crops, and we were running it through life cycle assessment models and trying to calculate impacts from that. One of the things that's interesting here though is I think there can sometimes be a tendency among scientists to say, oh, I've went out, I've done all my field trials, got all my data, I'm going to hand it to these people who do this modelling stuff and let them get on with it. That can be quite dangerous. And I think it's really important when you have a network like this one that people are fully engaged through to the end point and see the implications of what they are producing. Because in this work, I've got the global warming potential on the left-hand side. All of the energy crops give a massive improvement compared to natural gas on the global warming potential. On the right, you see the figures for eutrophication and acidification. Now, partly when I'm giving this presentation to the general public, I tell them that this is called using land. It's impossible to get away from. If you want to use land, then you get these impacts. And if you weren't using the land for bioenergy, you'd be using it for producing another crop, and you probably would have a similar impact. But that brings in the issue of what are we comparing with what? And LCEE specialists will talk about functional units, and the functional unit for this is the unit of energy. But there are other things in there. So do we also need a cross comparison on land? And behind these figures, there are a lot of assumptions about allocation, because this particular work was looking at stabilised sewage sludge and how it was used to provide nutrients. And therefore you can argue that actually you are providing a waste treatment and bioremediation function as well. And how do you value that? And should you put the impact on the energy outcome, or should you put it on the bioremediation outcome? So there's an awful lot tied up in that. And I think it's important that as scientists, when you get your results and data, and you hand them to the people who do some of this whole systems analysis type stuff, that you really keep a tab on what they're doing with it. And trying to bring that full circle and present these sort of results back to the people who were doing the work originally is really important. And that's one of the things we find in the hub, that bringing that back actually gets new questions asked and gives you new insights and allows you to refine methods in a way that's really quite helpful. Okay. So there are trade-offs. I showed two there on eutrophication and acidification. There are lots more. This is some work it's a lovely piece of work, I really like this, which we did back in, again, the SUPERGEN consortium. This only looks at electricity, and it has a number of different ways. I think we had about 20 or 30 different ways of producing electricity from biomass. And what this is a principal component analysis of the impact. So you're not seeing here the different ways of producing. It's saying I've taken every single one of those systems and I've measured its impact. I've measured it across all of these different variables. I have variables there to do with employment, I have variables to do with carbon savings, all sorts of different things. We then collate all of those and we say, okay, so we've got this overarching thing called biomass to electricity. What are the impacts actually like? And a principal component analysis, basically, if two vectors here are pointing in roughly the same direction, then they are co-aligned and they support each other. So the one that I'm going to point out is CS1, which is here. That is the figure for the net greenhouse gas balance saving over lifetime for a biomass to electricity system. And what is fascinating is that it points in the opposite direction to the figure over there on thermodynamic efficiency, Ecotoxicity, and a whole load of other ones down here. So if I try to optimize around a single parameter, let's say, because I'm from a climate change centre, I think that greenhouse gas thing is really important, actually I can do very negative things with respect to the others. And I just like this because it shows the complexity of it across some environmental, but also social and economic factors. That you can try to improve things on some of these factors up here, but you may make things an awful lot worse in the opposite direction. A reminder, there are many different types of impact. Up in the top here, I've put all of the ecological impacts that we considered in a project which was a number of years ago now. Over there I've got the economic ones, and down here I've got the social ones. I've framed it like this because sustainability classically has these three pillars: ecological, economic and social. But again, what I find interesting here is not where these sit around those three pillars, but the fact that the vast majority of them actually sit in the middle. They overlap. I would suggest that the network you have is focused on the environmental issues, but you cannot consider environment without taking account of these social and economic issues as well. They are inextricably linked, and by changing one you will change others. So in just the same way I showed you in that previous slide, that doing something that is environmentally positive can also have negative environmental impacts, you've got to be really careful as well about the social, economic and environmental interactions and trying to get those co-aligned. Uncertainty. This complicates things even further. This is a report that we did in the Hub on greenhouse gas balances. It's freely available to download. I had intended to bring in some copies, but I'm sorry, I was in Birmingham yesterday and didn't manage it. One of the reasons I put this in is to make the point that a network is about more than just research. And when we were quite early on in what we were doing, our advisory board said to us, it's lovely that you're doing all this research and it's very nice and we're all very engaged with it, but we do understand that it's going to take 2 years for you to get anything out of it. And actually we think you know quite a lot already, you just haven't bothered telling us so far. So what we'd like is, yes, please go and do all those greenhouse gas balances, but could you just tell us in a very short format what you already know? Now you would think that's quite simple, and we thought we'd communicated quite effectively previously. So we embarked on this document, and I put this together by starting with a meeting in Manchester, a 2-day meeting, and we brought in lots of people from outside the Hub. And a few pointers for networking here. Get everyone physically together in one place and get them to discuss the technical detail for a long time. That works really well. Then you leave and you try to write things up, and then it all goes rather pear-shaped. Because trying to keep track of 30 different people's contributions when they've all left the building is rather hard. So the number of authors narrowed at that point. And one of the things that happened is there are actually less industrial authors as a result, because the academics have a job here to do. And they're quite happy to continue contributing to this. But I think I only have 2 industrial authors left on there, despite the fact they were half the population in the room. And the report goes through answering the questions on the right. I'm not too bothered about that today. But it was hugely useful to produce that document and then to run a briefing session in London for policymakers over lunchtime for 1 hour to give them the key messages from it. And that has been the real value of this, and it brought people together from the different communities and made them think about where the gaps were. There is some work which has now been funded as part of a challenge project in the Hub, which picks up the gaps we identified in this and pursues them. So those are the sort of things that I think are important. If I come back to the technical, what that report did was it identified different sources of variation, and the one I'm going to focus on here is over on the left, variability in practice and yields, spatial and temporal. We don't need to go into the detail of that. The point is that the temporal issue is hugely important. I've mentioned already to you the timing of the GHG emissions is important. So we've now just managed to get from our flexible funding in the Hub a position where we're going to focus on that issue for the next year. The one above it is being picked up by UKIRC in what they're doing, and they have a number of calls which will be coming out of their flexible funding. It's also really important that your network looks at the UKIRC flexible funding, because there are many areas where I think it's particularly relevant to what you're doing. I had a meeting of the research committee there last week, and there will be a call coming out in about 2 to 3 months' time on that. Okay. Where we have this variability, variation, uncertainty that I mentioned, what can be appropriate is to use an environmental risk methodology. Risk is something that is innate to all of us. We understand it without thinking about it. But when we put it down mathematically, it's the probability that an event will occur multiplied by the magnitude of the impact if it does occur. Now, when I was in industry, I spent many years doing these assessments of risk, project risk really, for investors. And you can go through a very sort of standard framework and methodology for it. But some of the things that I think are important when we do this in environmental context are that the location becomes important and the carrying capacity of the ecosystem that you have. So yes, we can calculate environmental risk and we can go through and look at the probability that things happen, but we need to also look at the context in which a process is taking place. When we look at environmental risk and uncertainty, we're trying to establish how bad things might be. And that led on to this piece of work, which again is in a paper that was just accepted 2 days ago to Biomass and Bioenergy. And this again comes from collaborative work. It's people talking to each other. So one of my researchers in Manchester was talking to one of the researchers at Rothamsted who's got lots of wood chip piles, and the person at Rothamsted said, oh, we're getting a lot of very high levels of methane. We're a bit worried about microbial activity and so on. So then Miriam in Manchester was able to take that and say, oh, well, I could do that on my LCA work, and I could look at what the levels, if the figures that you have are correct, we could look at what the implications of that are. And this is quite interesting. So she used, as part of the risk analysis, we used a Monte Carlo approach to identify which parameters are key, and then went through examining the impact of those. And what you see here is, first of all, we find out that when we look back, actually, there is no data on the flux of methane from out with these piles. There's some data on what you have within them, but there's precious little beyond that. And again, this is something that we have just funded internally in the hub, and it's conversations between researchers which lead to us realising where our gaps are. But what you see here is, first of all, with no storage, then 1 month, 2 months, 3 months, 4 months. By the time we've got to 4 months of storage, if we believe the figures which are in the literature, which are the only relevant numbers we can find, then we could be looking at having total greenhouse gas balances that are worse than coal-fired electricity. Now that's quite worrying. I don't believe it, because I don't believe that in the real world any person who's managing one of these wood piles in industry would actually leave it sitting like that and go through the dry matter loss and the economic loss that would result from that. So another point, very important to collaborate with industry in order to ensure that you model things that are realistic and are going to happen in the real world. There is too much goes on with academics modelling things that are actually not ever going to happen in the real world, and therefore the impacts that they are suggesting are totally theoretical. So I don't believe it in that sense. We also don't believe the methane number, but it pointed to a hole in the data, and we now know that, and therefore we have Rothamsted looking at this much more closely. I'll just speed up a little bit. So I've talked about all these different impacts. This work took that environmental risk approach of multiplying the two things together to look at the impact for 36 different parameters. I'm back to soy in Argentina here, and it tried to plot them out. Put very simply, the blue circle is mineral oil. The purple thing is trying to do biodiesel from soy. If I have stretched the blue circle here, then I am being more sustainable, okay? And then I ask you the question, what's more sustainable, the purple one or the blue one? It depends, doesn't it? It depends on whether, from your perspective, climate change is the most important thing going. That's number one on there. And then, yes, it definitely makes sense to do soy and turn it into biodiesel. But if I'm interested in a whole host of other things related to biodiversity around the right-hand side, then I'm making a big mistake. So you need to take into account these trade-offs. It's my last bit here, energy policy. The other paper, which got just produced 2 days ago, which is a fabulous paper. Economic theory can be quite a dry area and quite challenging for many scientists. I really recommend this paper when it will be available in about a month or so's time, because it's written in a very accessible way. It's written by a lady at the Helmholtz Institute in Leipzig. And the way this came about was, we were at the European Biomass conference, we had a stand there, and she came and she chatted to us. Well, Daniela came and chatted to us. And we found we had some common areas. So then she sent one of her students over to Manchester the following year for 2 months. So we had an exchange that was long enough for her to become immersed in what we were doing in the UK. Now she had an objective. She wanted UK data to compare to German data in her PhD thesis. And she came for a 2-month period, and the objective was she was going to get this data, and we were going to write a conference paper. We put the conference paper in the following year, then it got picked up for the special edition, and that's where this paper has come from. So taking international presence at meetings, bringing key researchers over to the UK, embroiling them in all that we are doing, and this has been sustained because we have another researcher now from the same institute due to come next year, focusing particularly on anaerobic digestion. But it's important to have that international collaboration, and it's important to attend these things. The Hub attends, in a bioenergy area, the European meeting every year, and one thing I should say here is we're very happy to take stuff on behalf of different groups. And I had a BBSRC phone call yesterday, and we're going to take a lot of information, for example, on the BBSRC NIBs to the Vienna meeting in June. If we can take some material on the NRN cluster, I'd be very happy to do that. But it's about trying to bring different perspectives together, having the technical input, the climate change input, and bringing that with economic specialists from Germany is what enabled a really nice piece of work here. I don't think I've got time to go into the detail on it, but please read the paper. It's about how uncertainty affects policy instruments, and this is uncertainty in the science and also uncertainty in the cost. And you see two very divergent systems, the German feed-in tariff approach and the UK renewables obligation, and how those, it's lovely when you know what in your head what has happened and you know why has happened, and then you finally see the theory prove that this was correct, and that the hybrid process we've had, where we've had incremental change in policy mechanisms, was actually the right thing to do, and you can see a theoretical justification for that. But the marginal cost, MC is marginal cost, and we expected it to sit there based on our target, but by putting a price ceiling in place in the UK mechanism, what we actually ended up with was being over to the left instead. So we ended up with a higher marginal cost, sorry, because we didn't want to go higher on the actual cost, we ended up with a lower capacity being realised in the mechanism. And then the German situation was quite different, where we ended up with a very large increase in deployment, as we all know, with the AD system in Germany, but that the actual marginal cost involved is much higher. So it's fascinating. Implications of all that I've said to you for the NRN projects. This is my last slide. Climate change is important. I can't leave without saying that, really. It's very important. But you know what? Other environmental, economic and social impacts are important too. And from my days in industry, one of the things I'm always acutely aware of is that if you don't actually build something and do something, then you don't make a difference. So if it doesn't make economic sense, if it isn't a practical system, if you haven't built resilience in, then you've wasted your time. Whole systems analysis is really important, but it's got to be underpinned by detailed technical understanding. If you don't connect the people who know the science with the people doing the modelling, then you're wasting your time again. This is a tricky one. The consequences of multiple systems may not be the same as a multiple of individual system impacts. Quite a mouthful. You can look at one system, you can look at life cycle assessment, all that sort of stuff, but you then need a different approach, and you need to stand back when you look at what the implications are for Wales or for the UK. Environmental risk, I would really recommend looking at some of the environmental risk approaches in some of the clusters that you're doing. And another one, sustainability should be framed around stock and capital changes, not flows. It's absolutely pointless to tell me what the carbon intensity is or what the greenhouse gas emissions were, unless you also tell me at the same time what the capacity of my bit of the planet or my bit of the ecosystem is, and what I can actually allow to happen in there. And the last one, sustainability isn't black and white. You can't say, as I showed you with that spider graph, that that system's sustainable and that one isn't. Depends. Depends who you are, depends where you are, depends what you want. And knowing what you want is very key here. So that's the end. I've overrun slightly, I apologise. The Hub website is there. I said a little bit about it at the start, but please do look there for any other information and for a number of events, which I think will also be relevant to you coming up. I've mentioned we're going to Vienna in June, but we also have a number of events we'll be running in the UK this year, particularly where we're bringing European scientists over to try and build bridges in this area. So I hope to see more of some of you at some of those events in the future. Thank you.